Hi, hi everyone. This is a discussion of size reduction, just for fun. General aspects of size reduction. Let's talk about a bit about this. Applies to all ways in which particles are broken or cut. Solids are reduced through the process, different methods and different purposes. You could crush ores to a workable size, crush ores to release the material trapped inside. You could potentially grind synthetic chemicals down into powders or cut plastic sheets into fine pellets. Basically, size reduction is often done for purposes of meeting size specifications. Reducing particle size increases the reactivity of the solids. That's quite interesting. What happens is you often create fresh surface. You often create trapped reaction material inside the particle. Reducing size releases material for processing. Reduction prevents separation of unwanted material using mechanical methods. Reduction makes material handling easier. You have a reduction in volume. Then there's many other reasons for size reduction. Commonly, the machines are different ways. Compression, like a nutcracker. Compaction or impaction, like a hammer. Attrition, or rubbing, like a fowle. Maybe shear cutting. Anyway. The size range is very interesting. You're going from boulders the size of maybe 10 feet all the way down to microns, 1 micron or perhaps even less. And capacity is going in this direction. The larger the particle size, usually you're dealing with larger capacities. And when you get down to 1 micron, you are low capacities. And the energy per ton is also interesting. It's easier to break 10-foot diameter boulders than it is to break a 1 micron particle. Compression is used for coarse reduction of hard materials to give relatively few fines. Impaction gives coarse, medium, and fine products. Attrition yields very fine products from soft, non-abrasive materials. Cutting gives a definite size of shape, sometimes a definite shape with few or no fines. You take your shredding machine, it takes paper down to smaller strips, but there's very little paper dust generated. Convolution, you see the word minute in here, convolution is another name. Ideal crusher or grinder would have large capacity. Low power input per unit of product yields the size distribution desired for a single size. Performance evaluation, characteristics of actual equipment ideal unit, and accounting for these differences. The differences between ideal and actual are great, quite very large differences. Performance gaps have been not widely accounted for, even though there has been extensive study. Empirical equations for predicting performance are available, but theory is incomplete. And capacities of crushing and grinding machines are specific to the individual pieces of equipment. Product size, shape, and energy requirements are more common between machines and will be discussed generally. The objectives of convolution to produce smaller particles from larger ones. Smaller particles is desired for whatever reason, maybe their shape, maybe their size and number, maybe the freshness of the surface. Many chemical reactors have in-it grinding operations that produce fresh surfaces. Some machines are called crushers, crushing for a short period. Others are grinders, which grind for long times. Various machines and various names exist. Talk about efficiency. Efficiency is extremely low, basically. One efficiency measure is energy required to create new surface. And the efficiency index would be new surface created to the energy applied. That would be an efficiency index. Surface area increases greatly as you reduce particle size. The actual unit does not yield a uniform product, whether the feed is uniform or not. Usually the product consists of a mixture of particles of different sizes. Size range varies from a defined maximum, a definite maximum, to a sub-micron microscopic minimum. Some machines can control the magnitude of the largest particles. However, as we'll see a little later, the size of the fines are out of control. The common statement is fines are out of control. That may or may not be true, but generally speaking, fines are a pain in the neck or can't be controlled. Fines are minimized in some types of grinders, but not eliminated. Much, of course, depends upon feed. If the feed is homogeneous, the product may be uniform, but having varying sizes. If the feed is non-homogeneous, particle size in the product may vary greatly. Okay, you're going from the smallest to largest, it may be a factor of 10,000. There's an extreme variation in sizes. Okay, an extreme variation in size. Homogeneity may vary with size. In other words, smaller particles may have a different chemical composition than the larger particles. The large particles, the internals to a large particle may not be the same chemical composition throughout. It may vary. As a result, when you break them open, break these particles down, these large particles down, you may have different chemistries being exposed. Homogeneous needs definition, same particle size, same shape, same chemical composition, same physical structure. And the question is, what does homogeneous mean? The term average size may be quite meaningless. And some method of averaging should be defined. Different averages can be calculated. Polyhedron, the plane has sharp edges, corners may be impacted like squares or plates or needles. There's an assortment of different types of particles out there. You can have the typical granular particle. It's sort of spherical. Then you can have needles, and then you can have plates or flakes. Then you can have agglomerates, all kinds of different types of particles out there. For compact grains, the largest dimension may be the diameter, generally taken as the particle size. However, plate-like or needle-like, there may be two dimensions that characterize their size: the length of the needle and the diameter of the needle. The second dimension is important for, say, needles. The Reynolds number. Often, Reynolds number is probably not a well identified number in crushing and grinding, but it should be calculated for your machine. Very important to recognize the particle Reynolds number. It's the density of the solid. The particle could be the density minus the fluid of the solid minus the fluid density, could be. Diameter of the particle, velocity of the particle, and the absolute viscosity of the air or what fluid it's in. There's two major regimes, Stokes drag regime and the turbulent drag regime. And in the turbulent drag regime, particles move like objects. Right? They flow separated from the flow. And it's easy to hit a particle in the turbulent regime. However, in the Stokes drag regime, particles move like the fluid and are basically fluid particles. very slow motion in this regime. Difficult to hit a particle in the Stokes-Drag regime. Density is important in the turbulent regime, but not in the Stokes-Drag regime. Viscosity is important in the Stokes-Drag regime. You truly don't want, or most often you don't want to necessarily be in the Stokes-Drag regime because the ability to crush and grind may go down. There's also an in-between regime between Stokes-Drag and turbulent, which is often called the transition regime. And the three regimes have important significance in the design of size reduction equipment. The three regimes also suggest at least three different types of machines are needed to reduce baseballs to dust. One machine per regime. Machines that work on large particles will likely be inefficient on smaller particles. So size reduction machines change as you approach the smaller sizes. Different forces exist based upon the differences in the regime. In the turbulent regime, body forces like gravity are important. In the Stokes-Drag regime, surface forces are more important. Turbulent regime, density is important. In the drag regime, viscosity is important. For example, if you have a situation where you have substantial wall buildup, that's a sign of the action of what might be referred to as surface forces. A particle has a solid mechanical nature and a fluid mechanical environment. Particle breakage in the machine, both the particle and the fluid mechanics should be understood. The effect of size. Well, size does definitely matter. Size effects are significant in size reduction. 325 mesh or 45 microns has a different world from a 4 mesh or 4.75 millimeter particle. There is a difference of roughly 100 in length, a difference of 10,000 in area, and a factor of 1 million in volume. So you have definitely a distinction going on between large particles and small particles. Smaller particles, the smaller the particle, the more important the surface forces, or more important is the surface and therefore surface forces. More important surface processes become. Behavior of 4 micron particle is probably determined by its surface, whether there's static cling, whether there's agglomeration, flowability, discharge behavior, all dependent upon particle or impacted by the particle surface. Surfaces can also be easily coated, covered, poisoned with moisture, oxides, hydroxides, etc. So the surface properties and the chemistry of the particle may have little to do with the material inside the particle. An example of this behavior, it's hard to clean a fine particle mill, right? Hard to clean fine particle mills. Cost of power is a major expense in size reduction. Typically, size reduction machines, as we'll discuss later, are about 2% efficient, maybe 0.5% efficient. So a lot of power goes to simply running the machine, and the power that goes into grinding and crushing and size reduction tends to be a lot smaller than the energy went to the machine. Factors that control this cost are important. Particles are distorted and strained. Work is necessary to strain, and the work necessary to strain is stored temporarily as mechanical stress. Additional forces distort the particles beyond the ultimate strength. Sudden rupture occurs. Anyway, let's take a look at this. It's an amazingly simple picture, and it's also highly informative picture. First, you'll notice there's 3 impact points. All right. If I increase the number of impact points, suddenly the importance of single point becomes reduced significantly. And that you no longer have, say, you no longer have this occurring where there's a crack formation between two contact points, but instead you'll have, instead of this situation occurring, you'll have an abrasion away, abrasive, the surface will be abraded away. So you're looking for maybe 3 or 4 or 5 contact points. Above 5, going to 10 or long, you have less efficient type. I mean, the size reduction occurs by the wearing away of the surface. But if you look at this, you'll see three size particles being created. Below the contact point are the fines. This is where fines are produced. Between the 2 contact points, you have slivers being produced. And then this outside volume here might produce another particle, or this interior will also produce another particle. So you have fines production, intermediate production, and larger particles being produced. You'll also notice that the fines here, the amount of fines that are produced here depends upon the size of this contact point. In other words, if this was a knife edge here, there'd be a small production of fines. If it's a very large contact point, like a dull hammer, then this would produce a lot of fines. So what was interesting is that as, for example, in hammer mills, the sharper the blade, the smaller the contact point, and the less fines that are produced. The larger the contact point, the duller the hammer. Excuse me, let's say it that way. The duller the hammer, the larger the contact points. So the more fines are produced. That's counterintuitive. Dullness leads to more fines. That's counterintuitive. Sharp edges leads to less fines. That's counterintuitive. That's what actually occurs. Now, if you notice, we have 3 different particle sizes being produced. And then if you throw it out on a sheet of paper, you have the fines here, perhaps the intermediate particles here, and the larger particles sitting out here. Breakage of 8 millimeter diameter glass sphere. And according to mass fractions, right, you'll see these out here dominate most of the mass. And these in here will appear as this flat hump in this region. And the fines won't even show up. Now, well, they'll be in here, but certainly won't have an impact. Now, the fines have lots and lots of numbers associated with them. Fines come in high numbers, but they'll weight. Intermediates come in, say, intermediate numbers and have some effect. The major weight is carried by the larger particles. New surface created. The creation of new surface requires work. And again, we're getting to this area that efficiency is new surface area generated divided by energy input. Work is supplied by the release of stress energy when particles break. So a unit area of solids has a definite amount of surface area, surface energy. All energy stresses in excess of new surface energy created must appear as heat. In other words, if the energy doesn't go to breakage and the creation of new surface, then it will be going to heating the material. Now, there is an attempt at crushing efficiencies. And this is some definitions, crushing efficiencies, and you throw in an equation. And you're really after how much energy absorbed by a unit mass of the solid. That's what you're really interested in. So you have some sort of surface area per unit, surface energy per unit area times the difference between the product, the area of the product, and the area of the feed, and then divided by some sort of efficiency. And you get the energy absorbed by unit mass. Total mechanical energy is stored in the material. Surface energy created by the fracture is small. Most of the energy is converted to heat. Crushing efficiencies are very low. They range from 0.06 to 1%, very, very low. Significant portion of the energy goes to running the machine. The motor consumes some energy. The gearboxes and bearings consume some energy. And seals will consume some energy if there are any. So what you could possibly do is run an energy balance on your piece of equipment. You run it, you run perhaps the motor by itself, the motor with the bearings, and the motor with the bearings and gearboxes, and then you throw in the seals. So you have considerable amount of energy just simply running the machine. So you do an energy analysis on your machine, different components. And then you, that would be basically, the whole idea is you got the total machine, you run it empty, you get a background energy level or a background power level with a watt meter perhaps, and then you run full, and that will give you, running empty will give you these, and running full will give you these, plus the material. So doing a bit of a subtraction there, you could get an estimate, not a reliable estimate, but I mean, reliability is another issue. An estimate on how much power you're actually putting into the material. Right. There's been various empirical relationships out there. For example, this chap way, way, way back in time, 1867, Reynolds said the work required in crushing is proportional to new surface created. Efficiency is constant. Various quantities are combined into a single constant. So he said that basically, this is the constant. You have 1 over the size of the product, which will be a large number in comparison to 1 over the diameter of the small object. Small feed, excuse me, the feed, which is large. You have large feeds going to small product, so this will be a positive number. And then you measure the power to mass flow rate. Now this is the power difference, right, between running full and running empty, right? So you divide that by the mass, right? So you have power per mass flow rate, right, or energy per mass. See, power is energy rate, mass flow rate is mass rate. Anyway, product size is much smaller, so that means 1 over DSB is larger than 1 over DSA. The law is close to being correct. Is the closest to being correct among these types of laws. Applies over a limited range of particles, and K has to be determined experimentally. You might want to determine your K. Again, you run full minus running empty. Take the difference, you can figure out what power went to the material you're crushing. You got the size of the product and the size of the feed. So you could possibly calculate your K factor. Here's an example of that. We'll just leave that up for a while. You're going from particles of 0.75 down to particles of 0.2. You do some mathematics. The mass flow rate has changed somewhat. Wait a minute, this is the new operation. So you find out that you need 11.4 horsepower, whereas up here you were up at, well, you're interested in what the power consumption capacity is reduced to 10 pounds per hour from 12. And this is an estimate. Then there's Kirk's law, and basically he said that reduction is a ratio of the initial particle size to final particle size. So he has the product excuse me, the product here and the feed there. So this is going to be a positive number. And then you got power per mass. Flies over a limited range of particles. Law has limited utility. Then a generalized relationship where you throw in an n there. It's n equal 1 for Kirk's law, n equals 2 for Reynolds law. Then you have the bond crushing law. And you see the power per mass supposed to vary with some constant over 1 over ds. You got to figure out what ds is. All right. Let's see what ds is. That's size, basically. Anyway, I give you an example of its use. Product, 1 over product, particle size for the product, minus square root of particle size for the feed. Throw in your lead constant, and you calculate the power. Now, the lead constant, let's see where we have the work index sitting here. Okay, you'll notice that all the work indices are floating around the same number. 6 being the lowest, I guess 6.3, with 15 or 19 being the highest. So there's not much change. Factor 3. Specific gravity is floating around the same number. 1.4 for coal, 1.3 for coke, but those are the only low ones there. They're all 2 6s. Yeah, there's a 3.5 there, or 3.15. Anyway, give you an example of how the work index is sitting there. You got work index sits here, and you got the same size particles multiplied by this constant here, wherever that came from. And then you have perhaps 227 horsepower required for breakage, product, feed, anyway. Okay, now, when I say you measure power full and minus the power empty, that's for continuous operations. However, if you stop your machine and you leave material inside the machine, then the startup torque will be higher as well. Okay, so continuous operation is one value you should be concerned about. So power usage during continuous operations. And then you should be interested in is if you stop your machine or if you had power failure or whatever, and you're starting up a machine from cold position, then what's the power draw in that situation? Just some things to be interest to you. So there are no general laws available. Again, due to the variation of various machines out there in different size ranges, different energy usage, efficiencies, there's no reason to expect there to be a general law. Let's talk a little bit about the physics of breakage. It's a vast subject. Basic equations for breakage are not available. I don't know if that's true or not anymore, considering the sophistication of computer modeling these days. But we can say a couple of things. Complex cohesive bonds exist in solids. You got the molecules and you got the atoms, and they're ordered, they're arranged. You have repulsive forces and you have cohesive forces. They're in conflict or they oppose each other. There's a substantial cohesive force between sodium and chlorine. You got positive sodium, negative chlorine, and they attract each other by electrostatics. And then at the same time, you have two positives that repulse each other, again, to do electrostatics. And then chlorines repulse each other. So you have this electron clouds repulse each other. Nuclei repulse nuclei. All electrostatic forces. So the overall state of equilibrium exists. The equilibrium is supposed to be dynamic. Interatomic distances fluctuate. Thermal motion of atoms causes fluctuations. For a rupture to occur, you need about a 10% increase in distance between the atoms to cause breakage. Rupture is by tensile forces. Compression does not cause rupture. Okay. Shear also ruptures solids as layers of atoms try to slide over each other. Differential thermal expansion can cause rupture. I was doing a study, or trying to do a study of some waste material, which was an amalgamation or agglomeration of different types of metals. I was hoping to break apart the material with thermal expansion and contraction. Chemical attack, well, can stress bonds and aids in rupture initially, yes. However, if you're trying to do a chemical attack, it's not going to be fast enough to keep up with the crack propagation. So it can't move fast enough. So you have solids which are elastic and plastic together. And behavior is dependent upon material and the conditions. So we have stress-strain curve. Stress is proportional strain using Hooke's law. Personality constant is Young's modulus. Okay, changes in distance on molecular level is 1%. Very small changes. The material behaves as an elastic solid. So let's take a look at this here. So you have stress here, which is force over area. And this causes a change in strain, which is change in distance, basically, right? So you have stress strain, or force varies distance. I take force times distance, which are the units here, some of the units, as energy. And that's, the energy is the area under the curve here, okay? So, I also have the definition of stiffness here, which is the tilt of the angle. Now then, let's take a few different types of materials here. Let's take chalk, teacher's chalk that you write on the chalkboard. Now that the stiffness will be almost vertical. There's no give in chalk. What happens is it will reach its ultimate stress very quickly. Chalk has a very low ultimate stress, and it's easy to rupture or break. So vertical line, very stiff stuff, reaching the ultimate stress very quickly. Now, opposed to chalk, we have plastic. You take these chunks of plastic that you have at the end of your ballpoint pen, and they usually have some sort of tab on the plastic. Anyway, you can bend that thing back and forth all you want, but it isn't going to break apart. And that would indicate plastic. Example would be the tip of your ballpoint pen again. It has no stiffness or very little stiffness. It can tolerate huge amounts of strain, and the stress level may be intermediate to small. And you're likely not to reach the ultimate stress. The ultimate stress up here is where this thing breaks. Here it acts as a complete solid. And then there's, between this regime and this regime, you have a regime where there's a yield point where the matrix of atoms may move over each other, or they may become plastic mechanics, or there's ductility to it. Now, again, I said the area under the curve is energy. So let's go ahead and strain something. So we go up to this point. We don't reach the ultimate stress, so we fall back down. We go up to this point here, perhaps a little less, and we go back down. We go up here to maybe B area, and we fall back down. So we've just put in huge amounts of energy with each of those. the energy under the curve will be this amount, the energy under the curve, this amount. Anyway, at point B here, the energy is what's ever under the curve here. The energy did not cause breakage. However, the energy went into the solid, right? Got absorbed into the solid, and the solid heated up because of the energy addition. So obviously, one of the really neat things you can do is if you have a high energy input to your solids without breakage, just to monitor that the amount of energy that's being used to heat the material but not break the material. That's an inefficiency in the grinder, right? So not only do you want to measure the particle size of the feed and the particle size of the product, you also want to measure the temperature of the feed and the temperature of the product. And you have the mass flow rate, the temperature rise, the heat capacity. You get a measure of how much energy was wasted in not breaking the material. So that would be an interesting calculation you would do. Mass flow rate times heat capacity times the temperature rise. The temperature rise, you got the material broken. Okay, the material breaks, comes out. But the temperature rise of the inefficient energy may be high enough to melt the material or cause the material surface characteristics to change, and the material freezes back together again or agglomerates back together again. That's a really pain in the neck. You got the stuff broken, but it fuses back together again as part of the release. Isn't that a terrible situation? Which brings rise that if you have that type of situation, obviously you want to get rid of that energy. Okay, it's there, it's causing a lot of heating. Well, if you put a slipstream of liquid nitrogen in there, okay, that would keep the material from heating up. So the energy goes to crushing and grinding, the energy goes to heating up the material, but you put a slipstream of liquid nitrogen in it, or some CO2 chips, or carbon dioxide, liquid carbon dioxide, I don't know. Anyway, you can keep the material from heating up during grinding. Okay. This stiffness curve is also a function of temperature as well. At, say, room temperature is this curve. However, for plastics, it may be a very shallow curve here. So if I take a plastic and cool it down significantly, I move the stiffness up where it's vertical. So plastic room temperature may be down here. And when I change the stiffness on it by changing, quote, the conditions of the operation, I can cause it to be significantly increase in stiffness, which makes the ultimate stress more reachable in operations. And I would also, in such circumstance, also check to see the ultimate stress was changed as a function of temperature. So the slope of this line is a function of temperature. Also the ultimate stress is a function of temperature. So away we go. We got all kinds of little variations we can run on this diagram. And it would be interesting to know if you have this diagram for your material. All right. All you got to do is hit it with a force and see how much it strains, and then figure out what the yield stress is. And these are not some theoretical things. These are things you can actually measure if you spend a little bit of time at it. Okay. You do not, principle of engineering is you don't have to accept what's available. You can make changes to improve your processing. Okay, a gallon of liquid nitrogen costs $1.30. Again, you don't want the machine to run cold. You just want to have cold feed and then cold product. And as it comes out, it doesn't fuse back together again. So there's a lot of playing. When you have a curve like this, there's a lot of things you can do to change processing nature. Kind of neat. In other words, if you got something that you do not like, right, in engineering, you don't like the circumstances you're in, well, you just modify those circumstances to things that you do like, or processing that you do like. In my world, you get a no. Okay, you've been told you can't do that. Well, maybe you can. You just haven't figured it out yet. So in my world of engineering, there's no such thing as failure. There's no such thing as failure. And there's no such thing as a no, absolute no. You may run into no's along the way, but at the very end of the trip, you're going to get a yes. Just a matter of perseverance. Okay, second part of the curve, the metal bar flows, yield stress is reached. Then you display ductile qualities, behave plastically, atoms slide over each other. Then the ultimate stress is released, atoms refuse to slide, bar breaks. So let's see what we got here. We have the Young's modulus for different things and the ultimate stress for different things. There's no temperature given for this data because I would be very much interested in knowing how rubber will change with temperature. It certainly will get stiffer if I freeze it. And I don't know what the ultimate stress would be. And these carbon whiskers are supposed to be very stiff, I guess, and very strong, or what might be called strong. We'll get to that later. I guess this is actually strength. This ultimate stress is later defined strength. Fine particles are created below the contact points. Fines are produced at impact points. Intermediates are produced between impact points and larger what's left. More fines are produced from larger impacts than smaller impacts. So more fines are produced with dull hammer mill blades versus sharpened hammer mill blades. Impact points are larger for dull equipment. Dull equipment produces more fines. Sharpness of the edge can make a big difference in fines production. I said fines are out of control. They're, again, the engineering principle, if they're out of control, well, then get in there and control them, right? We have our famous picture, which I like a lot. Very simple picture, can be very useful in explaining things. Again, 3 contact points, there's the fines area. Or if I have 10 contact points, then I have abrasion rather than breakage across the particle. I have attrition along the perimeter. Okay, intermediate comes from cracks between the contact points and may have a different shape than the original material. Multiple contact points spreads the energy out and particles do not reach their ultimate stress. Cases of fewer than 3 contact points, the particle may escape breakage or pop out. So anyway. Size reduction is cross-disciplinary subject, combining solid mechanics and fluid mechanics. Fluid mechanics determines how a particle is going to be hit, and solid mechanics depends upon how a particle breaks. I suspect that breakage has focused on the solid mechanical aspects. Less attention has been paid to the fluid mechanical behavior the particles are in. Okay. Case in point, a baseball player can hit a baseball player can hit a baseball, a home run, but it's highly unlikely that a baseball player can hit dust. In fact, baseball players can't hit dust. When a bat comes swinging by, the dust just flows around the baseball bat. Case in point. Flow follower concepts in laminar flow lowers the efficiency of size reduction equipment by a significant amount. You should try to design your size reduction equipment and particles in the turbulent regime, right? And of course, hopefully you keep the same regime as you change sizes. Okay. If you keep the same regime as you change the nature or the size of your machine and keep the same same mechanics in the machine, then you'll likely having easier time and process scale up. Different from what we got granite here, and different from metal, but similar. Again, the different stages to fracture brittle. You have plastic behavior described as Young's modulus. At some point, the material starts to slide over each other. You have formation of open axial cracks, dilation of the rock. Strong changes in slope occurs. Strong changes in the slope of the stress strain curve occurs. Growth of cracks along grain boundaries. There you go. Forgot to mention that. This thing right here is for pure material. But now you got to recognize that what is meant by a pure material and what its nature is. This line could possibly change because of grain boundaries. One material has same material, same chemical composition, but different types of grain boundaries. Then you throw in flaw distributions in here. I will change this. So sort of like sort of like football where the field is open and the runner is scoring a touchdown. You got all kinds of things floating around out there. Growth of cracks along grain boundaries and fault fractures and the rock fractures rapidly. Case in point, a long time ago, my father said, my father was an engineer, and I hopefully has done as he would expect it of me. Anyway, he said, just made this casual comment, thank God coal is pre-broken. I said, what? He said, yeah, coal is pre-broken. And that's very true. If you've been in a coal mine, my grandfather was a coal miner. Coal is already pre-crushed by the motion, and the earth pre-crushes coal. So that makes the mining of coal real easy. So anyway, so we have strength and stiffness are different properties, right? Strength is measured by the ultimate stress. Stiffness is described by the elastic behavior. Little correlation between stiffness and strength. You have a broad spectrum of properties that exist. Easily ground materials, you're looking for high Young modulus, high stiffness, low strength. You want a low ultimate tensile strength. Requires little strain to fracture. There you go. Strain energy is product of stress times strain. We've already said that. If you look at the units, it's energy per area. Right, units is energy per unit area of cross-sectional area. Strain energy is the area under the AD curve. So you're looking at all the way up here. Right, D is where you have breakage. No more force is necessary. So actually the force drops away. But strain also sort of drops away. So this curve up here may not actually exist. I mean, the product material is no longer particle it once was. Strain energy area under the curve, elastic because it's the elastic portion of the curve, yes. You're riding up and down this curve, you impulse energy in, you impulse energy in, you impulse energy in, and that energy collects as heat. And hopefully that does not cause problems for you. Strain energy is not uniformly distributed, and it collects around weak points. Strain energy concentrates around holes where the radius of curvature is small. This is stress concentration factor, right? The local stress can be very much higher than the mean stress factor. I don't know, get rid of the word. Local stress is higher than mean stress. Now we have hardness. Hardness is the resistance to deformation. Toughness is the resistance to fracture. So we have the scale there. And we're shooting for brittleness index here, right? Brittleness index, which is hardness divided by toughness. So data are available. So something with a low brittleness index, it's difficult to come into, right? Index. High toughness example would be plastics. So plastics does not have hardness to it, but it is tough. So high brittleness is an indication it's easy to break. Now, crack propagation, that's kind of interesting. Oh, sorry, I missed out here. There's so many things that can happen to you. Oh, I went the wrong way here. Let's see what we got here. Sorry, I'm going to flip through here. I think we were around 54, if I'm not mistaken. Well, sorry, apologize. So we were here, now we're here. Now we're here. Now, let's talk a little bit about propagation, crack propagation in solids. Most solids have flaws, which cause weak volumes, dislocations, microcracks, crystal boundaries, incorporated impurities. When I was taking my high school chemistry course, I thought crystals were always pure. They're not. Crystals are pure only if you grow them very slowly. If you grow crystals very rapidly, they have a significant portion of impurities that are trapped inside the crystal. So you have grain boundaries, inclusions. Flaws are difficult to characterize. They're three-dimensional and they have unknown distributions. Overall stress around a crack has to reach a critical value to start a crack. Once started and the strain is not rapidly relieved, the crack will accelerate to high velocities. Strain is not rapidly relieved, so there's some sort of time in there, the strain. The speed can approach 40% of the speed of sound, so there's a lot of fast motion in here. Strain energy is relaxed during crack propagation, and new surface is produced. Strain energy is distributed to other cracks, which may propagate too. Strain energy exceeds the energy associated with new surface. If it doesn't exceed it, then you won't have new surfaces. Absolute fracture strength of a rock is very reproducible. It's interesting. Formation of final fault requires almost as much stress as that required to initiate crack growth. That's also interesting. Some of these are quite interesting statements. Cracks develop in the direction of other force contact points. We've already said this. The probability of breakage increases up to about 10. Above 10, the breakage probability decreases. And the cracks tend to run along the surface. That's called abrasion. Basically, you're removing the surface. For breakage across the particle, you need probably 4 to 5 contact points. And direct process applications, you've got to remove the fines. If you remove fines, then you don't have the 10. Breakage of large particles or larger particles is greater in the absence of fines. So you don't want to recycle fines if you're into breakage. What you want to do probably with some of the things you can do with fines is you capture them. You maybe wish to agglomerate them, send them, may wish to agglomerate them and send them back to the initial feed. You may use it to change the nature of your feed, which may not help you any, maybe a negative improvement. or a negative change. You may take the fines and agglomerate them into a new product, which is also a possibility. You know, it used to be I bought grass seed, right? Now I buy grass seed that's coated with maybe a insecticide, it's coated with fertilizer, is coated with mulch. So now I have a high-tech fertilizer, right? So you got a fertilizer company making pellets, and you got some fines where you take those fines over to the other part of the plant where you're making coated seeds, and they could be used quite readily into the grass seed coating. It's amazing how you take what we referred to as a waste stream. You can't call it waste anymore. That's not a great idea, because the government will come in and claim that if you have a waste stream, you're obviously polluting the environment. So you just want to call them a byproduct, right? Sorry, government. Anyway, it's really important how you say stuff these days. And you want to make statements that are to your benefit, to your company's benefit, and to your benefit. Rate of deformation, well, it matters, okay? An example would be you have a bar of toffee or whatever, saltwater taffy or whatever. You hit it, you can break it with a hard, fast, sharp tap, and it breaks. However, you can turn around and slowly bend it. So your rate of deformation can have a significant effect on breakage. Impact and compression are thought of being distinctly different, but no, they're not. It's just a matter they differ by speed. Impaction is very fast. Compression tends to be slower. And we got some practical velocities varying considerably with the type of machine. Roll crushers, roll mills, ball mills might be 1 to 10 meters a second. Impact mills, 20 to 200 meters a second. High energy mills, 500 meters a second. Change in velocity causes a change in the stress field of the elastic body. Each distortion caused by the force is distributed in the body as elastic waves. These are probably pretty cool to watch. I think there's probably some videos that show elastic waves on YouTube. Again, YouTube's fantastic. Internal reflections meet oncoming new waves, and stress levels change. With favorable reflections and additive effects, cracks are formed. Viscoelastic bodies, you are viscous and you are also elastic. So greater velocities mean less deformation and higher shear stress. Got to stop and think about that. In other words, apparently polystyrene is easier to crush by impaction than by slow compression. Got to think about that for a bit more. Then we have the effect of particle size. Internal stress patterns change as a function of size. Smaller particles behave differently than larger particles. 3 major factors of size is fall size and the distribution of fall size, stored elastic energy, and plastic deformation. Fall size and distribution. Fall size decreases with particle size. In other words, there's less flaws in smaller particles. The reason for that is the major significant flaws have already been broken. So what's left is less significant flaws. Exist as size is reduced, and the stress levels for breakage increases. The material becomes tougher, right? Smaller particles are tougher to break because they have less flaws or less significant flaws. Increase in the particle strength occurs as size is reduced. The more crushing work more crushing work is needed to break smaller sizes. So this business about small being tougher. There you go. Smaller particles appear to be more plastic than larger particles. This is tough too. Harder to put a focus force on a smaller particle. And an increase in importance of contact points occurs for smaller particles. Stored elastic energy effects. Well, energy is released during breakage. Energy released during breakage decreases with product volume. So as product volume decreases, energy released decreases. Energy needed for propagation decreases with the square of the area produced, right? So that's d squared. Now, if I take a look at energy released divided by energy needed varies as d. So when d gets larger, this ratio becomes larger. However, when d becomes smaller or drops, energy release to energy needed drops. So energy needed for crack propagation is not available at the smaller sizes. So cracks stop propagating at smaller sizes. More energy must be put into smaller particles for breakage. Plastic materials have to be impacted many times before breakage. Anyway. Plastic deformation becomes more important at smaller sizes. Smaller the particle, the more plastic it becomes. So you have something called brittle to plastic deformation transition occurs, or you give rise to what is called the grind limit. Important at millings, since it's difficult to cause breakage below the transition point. Smaller particles break from breakage of larger particles. It's very important to realize smaller particles come from the breakage of large particles. They do not come from the breakage of smaller particles. You don't have a small particle and you break it in half and have two smaller particles. No, that does not happen that often. What happens more often is the small particles are made in vast numbers during the breakage of large particles. Sort of like the concept of what is the size of the contact producing the fines, as we showed earlier. Anyway, let's see what else we got here. We got the famous grind limit that we're concerned about. Particles can be ground to a certain size and no further. That's the grind limit. And plastic particle size for transition of brittle material to fully plastic material is the grind limit. Equations are available to calculate the grind limit. Okay. Free surface fracture surface energies. Here's free surface is typically 10 squared to 10 third ergs per square centimeter. I don't know. Ergs is not a unit that I typically use, but here's some more ergs per square centimeter for glass, plastics, and metals. Temperatures. I can relate to temperatures better than ergs. If I create a crack, at what temperatures do you generate? 200 to 800 degrees centigrade. Calcite may go up to 1300. Glass. Quartz up to 4400 degrees C. So you can have very high temperatures that are very short-lived. They only occur. But what happens is there's such high temperatures that ignition points, not uncommon. It also indicates the nature of the surface can easily change on milling. Quartz in particular could change its lattice structure by a ball mill. So what chemically you're actually changing the composition or changing the chemistry of it. So you should recognize that. You should also recognize that, and say the tumbling in a ball mill, it can be a generation of static charge. And it can sit there and crush and grind away on your material and spark, and be sparking all the time. So sparks and dust don't go well together. So could have a ball mill generating dust explosions simultaneously being ignited by sparks generated by electrostatics during tumbling. If any of you hear this and actually have this happen, it'd be fascinating to take some videos of that. Really would be fascinating. Influence of additives. Many observed effects have not been substantiated. There you go. Lots of observed effects have not been substantiated. Moisture and temperature have some effect at low crack velocity. That's pretty speed of sound, isn't it? Anyway, low velocities usually don't happen in industrial process and practice. Again, we said crack velocities approach the speed of sound. The additives can't diffuse down the crack at such high velocities. So you wind up having no influence on energy by crack propagation. There is no magical additives in size reduction. No magical additives. Fluidity and flowability caused by additives. Now this may be a different story here. Grinding aids do increase fluidity of the slurries and flowability of dry powders. Chemical absorption on surfaces increase the mobility of particles and increase the probability of being cut in the nip, being nipped. Additives can cause a more uniform size distribution. That's interesting. Additives can cause the agglomeration. Agglomeration is a surface process, and what these additives will do is change the nature of the surface and will not agglomerate. An example of an additive that changes the nature of the surface and prevents agglomeration is powdered sugar on donuts. Donuts will agglomerate if there is no powdered sugar. However, with powdered sugar on donuts, you prevent agglomeration. Then you can eat the donut in celebration. Additives help in handling fines and handling fines buildup. Again, fines buildup is a form of agglomeration. To prevent that, you affect the surface. By affecting the surface, you prevent the agglomeration, surface of the fines. Additives help reduce wasted power. That's interesting. Additives can reduce power by 10 to 20%, or increase the capacity by the same amount. Viscosity control and wet grinding. Increased solids loading increases percentage of fines. Closer packing of solids increases the percentage of fines. Slurries with viscosity that are not too high, that's the trend. Reduction of viscosity by dilution is self-defeating. There's an important one. Sometimes when feeding operations, you dilute. And by diluting, you've just made your problem more difficult. So, chemical fluidity modifiers exist. We got Dow. Modifiers allow more dense slurries to interact with the tumbling medium. Now, there's oftentimes chemistry that happens in the lab that doesn't happen in the plant. This is often the case. There's a discovery in the lab, but it doesn't scale, stays in the lab. So you want modifiers to be effective at both the lab and the plant. In usual cases, they're only effective in the lab. Modifiers should not adversely affect downstream processes. Grinding additives cost maybe 12 cents to 30 cents a ton. That's not bad. And economically justified in the number of operations. Basically, a gain in production is far, far, far more important than the cost of the fines. Cost of the additive. Additives are essential for cold water slurries for replacing fuel oil. Grinding aid reduces water content. Some of these cold water slurries may be 96% solids, and they're flowing like water. It's amazing. General summary of breakage: more energy is needed to break smaller particles than larger particles. Fines are obtained at the point of contact. The rate of force application is important. Viscoelastic materials and plastics are best fractured at high speeds. Grind limit exists. Particle size transitions from brittle to fully plastic. Material occurs in high viscosity. Fracture energies are needed. Additives do not affect fracture physics. They do affect slurry behavior. Many forces to a particle that do not reach the fracture energy necessary to cause breakage. Much energy is lost as heat. The efficiencies are very low, 1 or 2%, we were saying. Process is highly complex. So, just some comments there. Got some questions here, which we'll go ahead and bypass. Let's go on to particle shape, size, and surface. Particle shape, size, and surface are fields of study on their own. We'll just outline some of the major features. Characteristics: shape considered independent of size. Size and surface are hardly related. Particle shape requires analysis. You may wish to run your operations to create a certain particle shape. For example, you may have particle shape that could be called a flakes. So greater hiding power becomes available with flakes. This is important in inks, paints, and cosmetics, for example. So you're shooting for grinding operations that produce flakes in this case. Next, you're interested in greater strength. Well, you get it with granular shapes, important in rubber reinforcement. Fibers are better than granulars for plastic reinforcement, and they generate a high impact strength. Smooth spherical grains give the biggest bang in explosives. Right? Again, particle shape and the effect on processing. Irregular sharp corners and edges can make explosive inhibitor unstable. Sharper regular corners and edges are important in abrasives. So you don't want sharper regular corners in explosives, but you do in abrasives. So there you have it. Now, good abrasives have high angular grains, low aspect ratios, no flat particles. Many other examples of particle shape exist. Here they are. Whole bunch of them. Okay. Some of the things you might wish to incorporate with your shape indices: flakiness, elongation index, angularity. Anyway, so let's go back. Sorry. Method of sieving. Well, if you ever sieve your particles, you're likely to see distinct shapes are found at different sieve sizes, right? Shape may actually be varying with size, and it's caught on sieves. Image analysis using shape recognition computers, obviously flexible, more advanced. Harmonic series are used. So here we have the original particle up here at the top, right here. And here we have the computer simulation. Okay. And what it's done is you have these simple shapes that you add on top of each other so that you can generate the particle of interest that you photographed. So these might be nodes, and you're adding different nodes to each other, overlapping them. And you have, this is your particle, and this is your computer simulation. This is the particle, this is your computer simulation. Anyway, looking at this, these are the harmonic amplitudes for glass, right? Glass particles. So you have the different harmonic numbers, and perhaps their amplitudes. Two extremes exist that influence the particle, right? Particle. Well, it's the material and the machine, right? One extreme is the character of the material has the most influence on shape. The type of material, type of machine doing the breakage has no influence. The other extreme is the machine type, controls the particle shape, and the properties of the material have very little influence. So reality is lying between the two extremes. In other words, the reduction ratio also has an effect. The smaller the ratio, the reduction ratio, the more cubic the material becomes. Little detailed research on shape factors in grinding is available. Material with strong planar structure will result in material being flaky. Materials from a bed of particles will be rounded. And close examination of relative effects of machine and material at different size levels needed. Characterization of shape is very difficult. Particle size, well, there's three definitions of size for an irregularly shaped particle. You have the first diameter, and that might be having the same volume. The diameter circle, that would have the same properties, and the linear dimension, the third would be the linear dimension of the same between particles. So you have these different particle, equivalent sphere, equivalent circle, and equivalent statistical, well, the definition of statistical diameters. Okay. 4 types of distributions that you got to recognize. Very useful. Number distribution, how many particles do you have? The length distribution, the surface area distribution, mass distribution, might as well throw in volume as the 5th one maybe, right? So all 5 of these should be looked at. Usually what we have, if we take a look at grinding operations, and we explain the initial feed distribution is right here, and quickly after a very relatively small amount of time, that distribution moves to some production of fines already, and the larger particles remain, but are less in size. So we have size reduction occurring. We have a broad distribution of some sort. Now we have a bimodal distribution of stuff. Okay. Effective grind time, effective time on grind product density for a nominal mono feed size calcite. Well, the time has been sort of mislabeled here. It's actually the number of revolutions, right? The number of revolutions is important. You have this as your initial distribution. It then becomes bimodal, maybe even trimodal, right? We were saying there was 3 different particle sizes. And eventually, long revolutions in the mill, it goes from a very broad distribution to a distribution way up here at the very end after 1150 rotations. Now, a couple of things you should recognize. It's not time that matters. It's rotations. It's what the particle has experienced in terms of physics, right? So whenever you deal with any rotating equipment, time is suspect, right? What you want to know is what was the number of revolutions that the material has experienced. Now, this is true for this grinding mill, but it's also true for mixing and stirred tanks. It's also true with rotary dryers. It's also true with extruders. It's true for a whole bunch of anything that's rotating or driven by a rotating pumps. Anything that has rotation to it, you need to worry about the number of revolutions that the material has experienced. Another example is take a look at your clothes dryer at home. You have on it a drying time, and you dry your clothes in 30 minutes. So the drying time of the clothes is 30 minutes. No, it's not. Well, it's 30 minutes, the clothes are dry. No, it's not true. And you do a simple experiment. Go ahead and put your wet clothes in the dryer. Do not turn on the tumbling action, right? Do not turn on the tumbling action, but to leave your clothes in there sitting still for 30 minutes. You will quickly find out the drying time of 30 minutes doesn't dry those clothes. So therefore, it's not drying time, okay? It's more like how many tumbles the clothes has experienced. Now then, I want you to test some dryers. And what do you think the number of tumbles there are in 30 minutes of drying time? Well, it's the rotational speed of the tumbling drum times 30 minutes. So that will give you the number of revolutions. And for any rotating piece of equipment, you should characterize the action on your processing material, the material you're trying to process, in terms of the number of tumbles or the number of rotations. Okay, it's not time that's important. It's what your material has physically experienced. So this distribution back here is typically referred to as a log normal distribution. Zero is absolutely zero, right? There is no negative particle sizes that can be created, right? Just like there is no negative radiuses for pipes, there's a hard zero right there. Anyway, number of tumbles. Now, what's also interesting is the concept that your process is actually taking place, okay? I'm a real smart person, right? I put my clothes in the dryer, turn the dryer on, I recognize the concept of tumbling, okay? And I have to deliver so many tumbles, so I have this in my background in my mind, and then I turn on the dryer for 30 minutes. After 5 minutes, I go and check. And the sheets are no longer tumbling freely, but have balled up into a ball. Now, this is a rare occurrence, but it does happen. And in clothes dryers, your clothes will ball up as, maybe a foot in diameter, 1.5 feet in diameter. But because it's balled up, the surface area is not exposed to the drying operations. Efficiencies are dropping off significantly in drying. The same thing with this mill here. You think it's following these distributions and it's going right on in here, but I have seen situations where you put in your 1150 rotations and the material has indeed broken down to a log normal distribution. So therefore, the process is actually done. Now, from 1100 revolutions all the way up to 2000 revolutions, this material has agglomerated. And now no longer does this distribution exist, but there's agglomeration that's occurred that moved the size of the particles to a larger. You may still have the log normal sitting there with the powder, but there may be a distribution of agglomerated material. Just because you have grinding doesn't mean it can also not agglomerate. This is particularly true if you're self-grinding material. Material will break down, go to a certain size, after which, because of static electricity created during tumbling, may actually increase. Pretty funny. It says tumbling, but actually it's an agglomerator. And many rotating equipment turns into an agglomerating equipment. Surprise, it says mixer on the outside of the equipment, but indeed, instead of being called a mixer, it's actually an agglomerator. it could be called a crusher, but in reality, it may be agglomerating. So you need to take a peek at your equipment every once in a while. The business about clothes balling up in your dryer seldom happens, but it does happen, okay, for whatever reason, okay. The reason for it, who knows? So, geez, it's an occurrence that does not frequently happen, so reasons or mechanisms may not be very well understood. But again, you got to watch out for what's happening in your process equipment. Okay, and this number of tumbles or number of revolutions is extremely important on any rotating equipment. Anyway, so that's what I say here. Increasing the speed of impacts is often the same effect as increasing residence time. This is the important one. The number of revolutions to reach a certain size is fixed. N theta, this is the rotational speed, and this is time. And the rotational speed times time is the number of revolutions. Particle size distributions are likely to pass through the same changes as breakage occurs or proceeds. This is often independent of the machine. Size distributions are influenced by the breakage strength of the particle, the magnitude of applied external impact energy, velocity measurement, the velocity magnitude of the impact. Okay, primary breakage, the large particle is are broken. The smaller particles are shielded from breakage and are stronger. You have the bimodal distribution occurs. Machine effects, well, smaller gaps lead to smaller particles for open circuit crushing, which we'll get to in the next presentation. This is kind of interesting. We have our old friend, our old picture, fines, intermediates, and you'll see this is for size distribution for a jaw crusher. It's kind of interesting. It's a function of gap or the opening. 9 millimeter gap lets 9 millimeter particles pass through. So there you'll be right around in there. Then 7 millimeters, you'll hear 5.3 millimeters, you're there. Each one of these have fines, right? Right. So D or the 5, this is the D, which is 2 millimeters. You'll see that you have a lot more fines being produced. You'll see. So the idea of the distribution as a function of different machine settings is kind of interesting. Right. Hope you all enjoy that. Closed circuit machines with classifiers, you can adjusting the classifier can change the output distribution. Now, a classifier breaks solids down into different classes or different particle sizes. So that's why it's classifying the solids. So we have impact tests on common salt. That's kind of an interesting thing. We use the pendulum to deliver the same amount of powder. So let's take a look at the results. So I have a single impact, and I have repeated impacts, but the same total applied energy. So my line for the single impact looks like this, and I see little production of fines. Now then, using the same amount of energy, but repeated impacts, same amount of total energy, I get a size distribution, which is here. And I see very large portions of fines, a much reduced size of the largest. So you can see that comparison size distribution for a single impact, repeated impact. So you see processing from the point of view of size reduction, repeated impacts more beneficial than just one impact. This is kind of interesting as well. Again, this is percent mass, undersized. So if I have low energy input, which is right in here, 11.11, and it looks like joules per gram, Got to calculate that out. At low velocities, I don't have much size reduction occurring. Right. However, if I go up to 18, factor of 880 times more energy, 180 or 18 or 100 times more energy, 180 times more energy, joules per gram, I have significant size reduction. Again, the particle size is a lot smaller, and obviously I'm operating at higher velocities. So I have impact breakage of crystal quartz over range of impact velocities. This is also interesting, right? I have a size reduction ratio, right, of 1.4, 1.9, 2.6, whatever, and I have the energies that are roughly proportional to those, right? So I have very low energy, very low reduction ratio. I have this distribution, and I don't have much fines here, but if I go up to higher energy levels and a higher reduction ratio, I have the distribution, this distribution here. Notice the distributions all have pretty much the same shape here. It's kind of interesting, and they all move together. Well, of course, it's a log-log plot, and there's a lot of things happening, but the shape is reproducible. If you can overlap those different distributions. Not so much here because this looks bowed. So size distribution changes as the grinding proceeds. Distribution multimodal, monomodal pattern generates with grinding, emerges with grinding, sorry. Whatever the particles feed, whatever the feed size, the distributions tend to coincide after continuous grinding. So it doesn't matter size distribution of the feed. After continuous grinding, they all merge. Repeated fractures produce more fines than a single fracture. With two fines distribution material, one coarse than the other, the larger particles of the coarser distribution will break first. That's interesting. With continuous grinding, the two feed distributions will tend towards the same product distribution. Okay. In other words, very high energy levels, these distributions will start to merge. Right. But down here, see, I doubled energy, or I put energy up by a factor of 10 here. The shape of the distribution tends to be same. Up here, I only tripled or doubled the energy distribution. Anyway, these shapes are the same. These size distributions are the same shape. That's what I'm saying in these statements here, sort of, right? The two feed distributions will tend towards the same product distribution. Now, very fine grinding effects, these effects are not present in coarse grinding. So you change particle size, you change the nature of the feed, you've went into Stokes' drag regime, and so you potentially have solid liquid bridging, you go into van der Waals forces, electrostatics, aggregation, agglomeration, influence of surrounding gases. So all kinds of things. You run into the grind limit, you run into plastic deformation. Interesting, increasing humidity decreases electrostatics, right? Increasing humidity tends to short out sparks, right? The difference between walking across the carpet in the wintertime, which is dry, versus walking across during the summertime, which tends to be higher humidity. You get sparked in the winter, less sparked in the summer. You also run into increased chemical reactivity with fine grinding. In this area, it's not, you got all these forces acting, okay? Different types of phenomena that occur. Not easy to be sure what forces or mechanisms are acting to produce a given effect in fine grinding. Here's a discussion of aggregation. I put these things together. I talk about agglomeration, but basically cohesion and van der Waals forces happen. And the material also affects agglomeration. So I don't distinguish between agglomeration and aggregation. They're pretty much the same gig. There's 8 or so mechanisms for agglomeration, and whatever mechanisms there are for aggregation, I just throw them in with agglomeration. It's just the way I do things. Agglomeration may cause a fundamental change in product. That may be true. Very fine grinding. Well, if you grind quartz, you can change the lattice structure. Apparently, you can cause a lattice distortion in kaolin clay. Materials with agglomerated easily tend to be difficult to grind. Red is not black and black is not red, right? Very easy to point that out. So materials that agglomerate will be difficult to grind. Agglomeration implies a coarsening of ground material. Both occur, well, agglomeration occurs. So you may think you're grinding, but indeed you've agglomerated. There are, what happens is you have an operation that's grinding away, and you reach a certain size, and then you put in stopping dust, and no longer grinds, but it agglomerates. You stop, well, you stop the grinding, and you anticipate agglomeration. To prevent agglomeration, you put in stopping dust. Stopping dust is a magical term for anything that prevents agglomeration. We mentioned the way you affect agglomeration is you poison the surface, right? Or change the nature of the surface. Powdered sugar on donuts, granular sugar on large cookies, just preventing hard candy. You put a coating of very fine sugar dust. Anyway, gives you some examples of agglomeration. Agglomeration is a particularly difficult problem in foods, right? Whenever you're dealing with foods. Increase in particle size with continued grinding because of agglomeration, right? Very dense agglomeration can occur in certain limestones, quartzes, and polystyrene under compression. A roll crusher, which we'll get into later, can actually turn into an agglomerator. Instead of crushing the particles, it agglomerates the particles up into a sheet. So watch out. Things don't happen the way you think they do. Effects of surrounding gas, increase in gas pressure, increases breakage rate. Well, that's interesting. This may be an effect of gas viscosity, which affects powder flow. At low gas viscosities, powder does not flow so readily and makes breakage difficult. So you have fluid mechanical behavior can occur. There appears to be an apparent grind limit for material in a particular mill. Same material may be ground to finer size in a nutrition mill. So if you're having trouble with one mill, you might try another mill. Right? You have a ball mill as opposed to a attrition mill. There's no chance, there's very slim chance in a attrition mill for agglomeration to occur. But ball mill, there's a chance. Equilibrium state exists. Smaller particles are forming larger particles as fast as the larger particles are disintegrating. See, an attrition mill will prevent larger particles from forming. So, mean particle size may be greater than the smallest mean size. High impact of compression may fuse particles together. That's interesting. One of the mechanisms of agglomeration is basically fusion or cindering. You put a lot of energy at point of contact. Okay, point of contact is a very interesting phenomena because the surface is a strange place. Surfaces are a strange place. However, at a contact point, I have the meeting of two surfaces. And that is even a stranger place where two surfaces are coming in contact with each other. So what happens, to give you an example of an experiment I want you to run, I want you to take two hot dogs, put it in a microwave oven, keep them separated, and heat them up. Get nice cooked hot dogs, no problem. Now then, I want you to put the two hot dogs together where they're touching at a contact point, and I want you to repeat the same experiment. You will note that at the contact point, there'll be a charred, basically the contact point causes the energy along the hot dog to focus at that one point for some strange reason. And you got energy coming in from one hot dog, and you got energy coming in another hot dog. That makes twice the energy at that contact point and a small volume. And it's extraordinarily different behavior than keeping the two hot dogs separate. So that gives you a study on cooking hot dogs together and separated. Anyway, let's see what else we got here. Mean ultimate size may be greater than the smallest. Oh, we already said that. High impact, fuse particles together. Yep. Smaller particles are more plastic than larger particles, which aids in the fusion process as one of agglomeration. Upon reaching the grind limit, further size reduction only changes the particle shape. That's kind of interesting. No further size and changes in size will occur. Plastic brittle transition should be correlated with grind limit. Correlations exist, but not an exact correlation. Other factors as chemical reactions, electrostatics, humidity, and various possible surface effects may occur. Again, the surface is an unknown quantity. You may think that you know the chemical composition of the surface, but that may not be true. There's 8 different surface chemistries that commonly occur, and you don't realize that. Plastic brittle transition is volume, whereas agglomeration is surface phenomena. Particle size distributions. Well, anyway, there's a wide range of functions. Early equations were very simple. Need flexible systems which tailors the breakage, tailors to the breakage process. There's a number of them. No two-parameter equations satisfy size distributions that are produced. So what do we have? Well, best one is truncated log normal. Basically, you have log normal distribution, okay. But the truncated log normal distribution, break it up, i.e. truncated. So here I have 4 truncated log normal. Here's my distribution right down here. I got this, and then it goes up there, it goes up there. So the theoretical curve, well, that's, and I have 4 log normal distributions. I have this one, then I have this one, and then I have this one. Anyway, here I have 2. So the idea of breaking up the distributions in different areas makes perfect sense. The matrix approach is kind of interesting. Okay, I have a feed distribution and I have the product distribution. So I have a feed vector. These numbers vary with different sizes, right? I have 10 micron, maybe this is 50 micron, this is 150 micron, blah, blah, blah. And we have the product vector, which is over here. So breakage is described by a matrix, a fraction of J, which breaks into size I. So J breaks into I. So J represents the size of the original particle in the feed, and J, that would be, and I would be the size in which the product element falls after breakage. So you have a breakage matrix sitting here, right? And then you take that times the feed, and then I'm not quite sure. I haven't done this work, but you have zeros up here, which makes the breakage matrix solvable for, basically. There are n-1 equations, and then there's n-1 unknowns. And basically, you have the distribution of the feed, and you have the distribution of product. And all you got to do is multiply by the inverse of this product matrix, or this breakage matrix, to see. You calculate just to see what values you come up with. Anyway, it's interesting. Unknowns can change as breakage unfolds. Approach has to be expanded to include agglomeration. Other effects, agglomeration. Much is not known. So what's interesting, I was telling you, maybe I've told you, I go ahead and tell you, there's a Stokes drag regime, and then there's a fully turbulent regime. And you quickly see that particle size measurements are actually broken up. You have the Stokes regime, or the Stokes diameters, okay, and then up here you have the more turbulent diameters up here. So even although these end off around 60 microns or so, whereas these will, I'm a bit hesitant to say that sieves actually work at 5 microns, but anyway. Interesting table. Different techniques, different sampling, and the range of the approximate range of sizes measured. Surface area plagues engineering. I don't know if you realize that or not. Let's go back to the word area plagues engineering, right? Most solids have pores, cracks, fissures, and grain boundaries, and surface area analysis is very difficult. The pores have surface areas, cracks have surface areas, fissures have surface, grains have surface. Direct measurement of areas very method dependent. All kinds of areas. Areas, who's got the areas? And surface areas, plague engineering. If you're dealing with surface area measurements, then you really only are relative surface area measurement, depending entirely on how they're measured. There's no one definition. Okay, any value should be accompanied by a statement of method of assessment. Practical measure, air permeability, gas absorption, various things. Flaws. That's the way you determine whether a gemstone is built by nature or whether it's built by man. Flaws typically indicate that it's a natural gemstone. Emeralds are notorious for the flaws or fractures that are in the gemstone. I'm not sure what they call it. I think they call it a jungle or something. Anyway, you can make emeralds flawless. There's no problem with that, i.e. Man-made emeralds. So you buy natural emeralds, they're very expensive, but you can buy the same man-made material without any flaws. So go figure, huh? The more flaws, the more valuable the stone. What do you think? I don't know that much about emeralds, but I do know that much. Flaws are randomly distributed according to some distribution. I don't believe that. It's only one type. Flaws often have a preferential direction orientation, perhaps. Flaws are specific to the process, that's true. Look at flaws, take pictures at different sizes, see if flaws change with particle size. You better believe they will. Attempts have to be made to relate physical properties to breakage, i.e. that's flaw distributions help. One relationship links probability of breakage to the number of stress. So anyway, much work is needed. And right now we'll stop at this point. Anyway, happy crushing to you, and I appreciate your participation. Again, my email. Probably the best thing to do is there's a blurb at the front of these videos. It's best to see if I left any contact information. I'm fairly old, near retirement, so I may not be at the university. Very good book on crushing and grinding. Most of this presentation was taken out of that book there. It's, I don't know, 600-700 page book, and stop to think about it. 600-page book. Okay, if you read 10 pages a night, how long does it take to get through the book? Well, simple math says 60 days. So you can consume textbooks fairly rapidly. You can use them as a tool to put you to sleep at night. And it just requires a little bit of discipline. 10 pages a night's not that hard to come by, but perhaps you're not so disciplined and you read 5 pages a night. That's 120 days through a book. And think about the information you can gain. Help you in your educational process. Just a comment. Then there's the famous book, McCabe, Smith, and Harriet. It used to be just McCabe and Smith, and then Harriet was added on. I think there's a 4th author nowadays. Anyway, now there's a second video on crushing and grinding, which will come up. And I appreciate you attending and watching this all the way through. And I wish you a good evening or good luck. Thank you very much. And we'll stop here.